ऑप्टिमल जनरल क्लासिफायर, ये अपन ने किया है अभी क्लासिफिकेशन। बायस वेरिएंस ट्रेड ऑफ अपन को अभी करना है। एंड इसके बाद जो है एग्जांपल भी इसी का है, प्रॉबेबली ओके अप्रोक्सीमेटली करेक्ट पीएसी लर्नेबिलिटी। ओके पीएसी लर्नेबिलिटी जो है ये एक चीज़ करानी पड़ेगी। ये बीसी डायमेंशन तो ठीक है, ओके ठीक है। ये वाली स्लाइड में लॉजिस्टिक तो नहीं है, इस वाली में देखता हूँ 21 जुलाई वाले में। बेस्ड डिसीजन रूल एस्टिमेशन मेथड्स मैक्सिमम लाइक्लीहुड एमएलए, अच्छा है ये वाले भी करने पड़ेंगे। ये भी फर्स्ट यूनिट है कि सेकंड यूनिट है? ये तो सेकंड यूनिट है, ये है ना। 21 जुलाई से जो है वो सेकंड यूनिट है, तो दैट्स नॉट एन इशू। आज अपन फर्स्ट यूनिट फिनिश कर दे रहे हैं, ठीक?
ओके सर, ओके
ओके। हाँ, तो आज इसके अलावा एक चीज़ और करनी है अदर देन दिस, व्हिच इज लीनियर रिग्रेशन। ठीक है। ओके, फर्स्ट ऑफ ऑल एनएफएल थ्योरी व्हिच इज नो फ्री लंच थ्योरी, इसके बारे में बात कर लेते हैं। नो फ्री लंच थ्योरी, ठीक है। Now the thing about no free lunch theory is कि it basically says कि there is a balance between the best versus fastest, है ना? There is a good balance. You have to maintain balance between best and fast. There is no way to get there is no one algorithm. Like let's write it down. There is no one algorithm that is best for any problem. तो प्राइमरीली द होल एनएफएल थ्योरी जो है ना, इट इज वेरी मच डिपेंड, आई मीन इसका जो इम्प्लीकेशन है दैट इज वेरी मच अबाउट कि ये बायस वेरिएंस ट्रेड ऑफ जो होता है अपना, कि whether we can like train too much, train too little, or can we find very complex models, or can we find very simple models. So there is like a good balance between simple versus complex. Simple models are faster, complex models are slower, but they give better. So this gives better results. Better results. But these are slow. These are fast, but they give like they're usually they have error. They have error. Okay. So there is a balance between model being simple and complex, right? And there is also like fast and slow part that I was saying earlier. है ना? So is this much like, does it make sense? Like you can either choose the fastest or you can choose the slowest, but both of them have their own things कि ये वाला इसमें अच्छा है तो वो वाला उसमें अच्छा है ना? Okay. So that makes sense, right? So far, good.
यानी कि कोई एक यूनिवर्सल एल्गोरिथम नहीं है जो दोनों चीज को जस्टिफाई कर सके।
Yeah, there is like for every single problem, like that's also this statement, there is no one algorithm. Basically there is no one single algorithm that can solve all of your problems in the best way. So there is no what do you like in certain sports we have like, you know, for example, when you're solving Rubik's cube and stuff, there are things called like God's algorithm and devil's algorithm, like something which goes through every single problem. So that doesn't exist, like that's just not possible for that to happen. There is no one single algorithm that will be fastest for every single problem or the best for every single problem. So that's that, you know, thing between this. That is what no free lunch theory is. So let's talk about the implications of this. The biggest implication of this is that you have, when you are optimizing, so when we optimize our code, we have to look at it from case by case basis. Case by case basis. We have to decide what is better. We have to basically, and under this, we have to decide speed versus accuracy. So this is what we are deciding, basically speed versus accuracy, right? So that is the primary implication of no free lunch theorem. It means that if you go towards the speed, you lose accuracy. If you go towards the accuracy, you lose speed. Like there is nothing, like you can't do anything about both of them. So that is how small the no freelance theorem is. The thing is, over this one concept, we also have the bias and variance. Bias and variance. Now, suddenly, we will have something that is a little bit confusing for people who have learned a bit about neural networks. So, if you have like learned neural networks, so artificial neural networks, you have some understanding of what a bias is, but that is not the bias that we are talking about, right? Like I said, like in the last class as well, and like the other day as well, that there is there like multiple people study these things and they all name everything according to their own जो उनको पसंद आया उनने वैसा नाम रख दिया, that kind of thing, right? So bias over here actually means error when it comes to, so what we call error in ANN is what we are referring to as bias. What it means is whatever our expected value was, expected value, or we also call it target, minus, so we subtract from this the output. So the output for our model, that's what we are doing here. So this whole thing is called bias. So this is called bias. This is also called error. This is also called noise. This is also called one more thing, loss. Did I write loss anywhere? No, yeah, this is called loss. So these are what it is. This is everything that it is called, right? It basically means we trained a model. So there is a machine which classifies certain things. We give it something and it classifies it as something. So it might be, so we give it X. It might put it in a bucket A, or it will put it in a bucket B. It can classify it like that, right? Now the thing is expected. If X was expected to go towards A, but it was sent towards B, so that is called the error, right? So how far away, so this is like very discrete, so just there's two choices, but it can be like a scale where you might want to classify something on a scale being like, give X to a machine. So you give X to this machine, and this machine can classify it on a scale this big, and you can be like, okay, the output falls here or over here or over here. So imagine if the expected output was over here and the actual output came out over here, the difference between these is called the bias as well. So this is an example of continuous thing where you can see an error. This is like discrete. So that is what error is. So is error clear to you guys now? Error makes
जैसे
sense.
सर सर जैसे एक एग्जांपल मेरे को जो समझ आया रिलेट करता हूँ.
Mm-hmm.
सपोज दूसरे पॉइंट पे हम क्रिकेटर बॉल मार रहे हैं, हमें
Mm-hmm.
सेकंड पॉइंट पे मारनी थी, जैसे
Mm-hmm.
कार खड़ी है,
Yeah,
हमें
yeah,
उसको टारगेट करना है.
yeah,
अगर हम उसको टारगेट कर रहे हैं पर वो उससे पहले ही गिर जा रही है,
yeah, yeah.
तो जो इन
So
दोनों
how
के बीच का
far away
डिस्टेंस
from?
है वो बायस बोलेंगे.
Mm. Yeah, yeah. How far? So if this was your target, say this point was your target on the car, and the cricketer ends up hitting like over here on the
हाँ
ground,
हाँ
right?
हाँ.
So this distance will be called bias.
अच्छा.
Bias, error, loss, whatever it is. So cricketer is the machine. Cricketer is this machine in that case, and ball is the input, and like the target where it hits is the output. Makes
चलिए.
sense, right?
हाँ हाँ. ओके ओके.
Yeah. So this distance, by the way, this distance is what it is. How far away it is. So that is what bias is, right? And let's talk about variance quickly. Now, what is variance in general? Like variance is how, so for example, if I was targeting a stick where I wanted to throw something on this stick and I was targeting this center of the stick, but sometimes I will hit over here, sometimes I will hit over here, sometimes I will hit here, sometimes over here. So this will be like a variance, like how far away it is from our target on both ends. That is what variance is, like how far away our data points are from our target. True? Makes sense? That much makes sense to you guys?
यानी उस टारगेट से हम कितना आगे जा रहे हैं और क्या कितना
Yeah.
पीछे फिर रहे हैं.
Maximum before it and maximum after it.
तो इनके बीच का डिफरेंस होगा वो वेरिएंस होगा.
Basically, so if imagine this is the target, right? And
हाँ
this is something that I hit somewhere, and this is somewhere I hit. This is also somewhere I hit. So this is like a distance, or this is a basic error between these two. This is also the basic error, and like this is also an error.
हम
But
एवरेज
this is
निकाल
the
सकते हैं.
consistent. Yeah.
एवरेज निकाल सकते हैं एरर्स का?
No, not an average. That would become like something else. This is like the largest one, like the how furthest away it is,
हाँ हाँ.
right? So this is the furthest away. This is the longest distance, and this becomes our variance here.
ओके.
So maximum how far away you can be from your target.
मैक्सिमम फार अवे.
Yeah.
ठीक है सर, ठीक है.
Okay. So that is variance. So now we kind of understand what bias is and variance is, right? Does that make sense so far? These two terms? Good. Now imagine you have certain things that you can have. You can have a high bias, which is like a lot of error, being off the target a lot of times. You can have low bias, which means you're on the target a lot of times. There is similar thing with variance. You can have a lot of variance or you can have low variance, which means that your target is being hit perhaps, but you are also going up very far away. Like your losses are or biases are like very big at times, or it is very small at times if variance is low, right? So doing this, what will happen?
रिपीट करो सर. नहीं.
Okay, okay. देखो,
कंफ्यूज हो गया.
bias कम और ज्यादा हो सकता है ना, एंड वेरिएंस भी कम और ज्यादा हो सकता है. बायस ज्यादा होने का मतलब होता है कि हमारा इन जनरल एरर बहुत ज्यादा आ रहा है, और बायस कम होने का मतलब है कि हमारा इन जनरल हम टारगेट को ज्यादा हिट कर रहे हैं, है ना. एंड ऑन दी अदर हैंड वेरिएंस बस इतना बता रहा है हमें, इफ देयर इज हाई वेरिएंस, यानी कि हम टारगेट तो हिट कर रहे होंगे शायद, बट मोस्ट ऑफ द टाइम वी आर लाइक ऑफ द टारगेट, है ना.
ये
बट
नियर बाय पहुंच रहे हैं पर कर नहीं पा रहे हैं.
हाँ, now इसको है ना, I will explain with a diagram actually. This
हाँ
will like make a lot more sense with a diagram.
ओके.
तो हम यहाँ ना क्या करते हैं, टारगेट बना देते हैं. एक यहाँ बनाएंगे, एक यहाँ बनाएंगे, एक यहाँ बनाएंगे और एक यहाँ बनाएंगे. Now the thing is, let's label this as, let's make this low bias, let's make it high bias, let's make it low variance, and let's make this one high variance. So this is kind of like a table. So low variance means and low bias. First of all, let's talk about low bias का मतलब क्या होता है. Low bias means that you are not missing the target a lot. So you are not hitting over here. You are hitting like over here. True? Make sense? That is what low bias is. Like there is less error. So you are
हाँ
hitting
हाँ
over more often.
हाँ.
And with low variance, it means कि wherever you are hitting, you are usually hitting in a group. Like it is like every single time you are hitting, it is like very much close to the target with low bias. So this combination of low bias and low variance is like you're always hitting the target. And most of the times you're hitting the target, right? And this is like a good condition. Make sense?
हाँ.
Yeah. Now, if you have high variance, but you have low bias, which means that you are hitting the target often, but at times you are also going outside, like you're not hitting the target sometimes. Make sense?
Yes, yes.
Okay. Now, when we talk about high bias, which means that we are off the target, यानी हम target hit नहीं कर पा रहे हैं अपना. तो and then there is also low variance at the same time, which means हम जहाँ भी hit कर रहे हैं वहीं आसपास ही hit कर रहे हैं. So it might look something like this, like there is a, like all of your predictions are off, but they are all together, like grouped together. Make sense? ये वाला? Good.
हाँ सर, हाँ.
And finally, हाई वेरिएंस एंड हाई बायस, यानी एरर, यानी हम हिट तो कर ही नहीं रहे हैं, हम यहाँ वहाँ हिट कर रहे हैं, बस अपना टारगेट नहीं हिट कर पा रहे हैं. And high variance just means कि we are like hitting it like further away, like each one of these points are further away from each other and not grouped together. So far make sense चारों चीजों का?
ये फोर्स वाला दोबारा बताओ सर.
Basically we are not hitting the target because there is high bias. High bias means high error.
हाँ.
So we are not able to hit the target.
परफेक्ट
At the
परफेक्ट सर,
same
समझ
time we
गया.
are also not grouped together.
समझ गया, समझ
है
गया.
ना,
ओके.
predictions are very much फैले हुए हैं यहाँ वहाँ, है ना.
कूल कूल सर, कूल.
Okay, now इसका
Is
implication
this like precision versus accuracy?
kind of like that, yes. तभी अपन we started from NFL, क्योंकि that is all about precision versus accuracy, है ना. मतलब
Okay,
precision
got
versus
it.
accuracy, no, more like speed versus accuracy, sorry. It is more like speed versus accuracy. So from NFL we have like these things that are part of NFL, and from this we have one more implication, which is called the trade-off between bias and variance. So let's quickly talk about that now. So should I even write it like this? Okay. Mm, First of all, let's just write the like heading, bias variance trade-off. Bias variance trade-off. And these all things, by the way, these three things are like interconnected with each other. Like they're very much connected to each other. Now, if you look at bias variance trade-off, what you have to primarily understand is that there is something called model complexity, and then there is something called bias. So bias error, like let's just write it down as bias or error, right? Now let's think about a model that we have started training, and with the model complexity, this is like low, this is high complexity. If we have started training our model on a data set, if we train that model, the error becomes lower and lower and lower and lower and lower. Eventually, it just planes out, like becomes stable. Makes sense? But here's the thing: the more you train the model, eventually over here, there is no return. Like if you train this model anymore, the complexity of the model will get higher. The machine that you are creating will like be very good with, it will become very good with giving you the right results. But the complexity, there will be like more parts to this machine. Like you will be adding very like a lot of parts to this machine at the same time. So complexity is going higher. Now, on the other hand, what happens is the more you train this model, it will become more used to the data set that you have trained on. So this specific thing might have a data set that it has trained on, which might be like say 10,000 some data points that you have trained it on. And you keep on training on those data points, and it will become very good at predicting values from this data set. But at the same time, what happens is if you take a random data set away from this, and with this more and more training, what happens is like it will lower the error eventually. But if you train the model too much, let me make this properly. If you train the model too much, after some point its accuracy will drop. And the reason for that is because it is becoming better and better with this data and not this other data set that we are testing it with. So this data set is like test data set that we are using. So our machine has become very much accustomed to this data. But if we give it any new data, कोई नया data दिया जैसे ही उसे, if it is like too highly trained, then it will give you bad results. But if there is a balance between these two things, like there is a point where you can train it on certain data, and you can expect the same result on this data set as well as any new data that comes. So that point over here, this point over here, this is called a trade-off. Now the thing is, you have to understand कि whenever we are training our machine, whatever we have trained, this machine that we have created is only being trained on this data. Just remember that for this. ये जो ऊपर वाली line है, this line that I've created above, this is only for random data that is outside this data set. So this upper line is random data for testing, random test data. So we can test it with data that is not part of this set, and you will get this kind of result, the one that is above. But if you were to keep on training this model on this data set again and again and again, then it will only become better at predicting this data, but not random data. Make sense so far? Okay, wow. I didn't expect anybody, like, I didn't expect you guys to like understand it in one go. That is very good.
So एक बीच में कॉमन पॉइंट है जहाँ हमें जो मतलब वो बेस्ट पॉसिबल रिजल्ट देगा आपने.
yeah.
सिंपल है, अगर ज्यादा कर दिया तो समझो ओवरफिटिंग हो रहा है. यानी कि वो डेटा को रट रहा है.
वो डेटा को रट रहा है, एग्जैक्टली वो डेटा को रट रहा है.
और अगर कम कर दिया तो वो डेटा को समझ नहीं पा रहा है, मतलब अंडरफिटिंग का मतलब
डेटा को नहीं समझ पा रहा है.
हाँ,
बिल्कुल सही. दैट इज द परफेक्ट एनालॉजी, है ना? तो दिस इज व्हाट बायस वेरिएंस ट्रेड ऑफ इज. नाउ यू कैन काइंड ऑफ गो बैक इस वाले पार्ट में, नो फ्री लंच थ्योरी. दिस थिंग इज सेइंग द सेम थिंग. Basically, you can either become fast or you can become better. So model that is on the left hand side, these models are fast because they haven't trained a lot. They are like simple models. These models are very slow. But these models can give you better results. Like over here it can give you a better result, but not on random data. So there is this trade-off here. This is the point of that. So no freelance theorem says the same thing. The whole bias and variance, where's that part where I was making it, this part also says the same thing. Like you can have a low bias with low variance, but it requires this. Now let's add a few things here. This requires that you train specifically on a data set and you test only from that data set. That is how you achieve this low bias, low variance. Usually, what happens is you end up somewhere around with high variance and low bias, somewhere in the middle, which is like very good. Somewhere in the middle of these, you want low bias. I mean, you want low bias. This is not what something you want. You don't want error in your models. So over here, you want something in the middle of this low variance, high variance, somewhere in the middle. You don't want this. This is like too complex and this is like too simple. So somewhere you will find a result where like you will find data, I mean your predictions around the circle like this. So somewhere between this and this, right? This is also saying the same thing, and this is literally saying that same thing on a graph. Make sense? So yeah, that is.
Can you explain that diagram again? I didn't like sync these graphs with that diagram.
Wait, this diagram or this one?
The above one.
This one, right?
This
Okay.
one, right?
Yeah.
Where the trade-off I can see in this.
Okay, that trade-off. It's just like let's say I'm gonna remove this. So basically, what I'm talking about is there is some point where there is the the error is like it becomes lower and lower and lower the more you train, right? So we are not as much concerned in this one specific diagram. We are not as much concerned about bias. Primarily, we want low bias, but what we are concerned about is variance. If we go towards this direction, doesn't matter if we go towards like this direction in this row or in this row. The moment you go towards the right, the model complexity usually is like going. It's going to be simpler. So simpler over here, and it's more complex over here. The reason there is a low variance in this area, by the way, like it is off the target obviously, but there is a like low variance, which means that your model has found a local minima somewhere in your function. So it's like, there is a local minima over here, so let's put everything around here. Anything that falls here goes into that local minima. That is the reason why we get this. But on the other hand, if you're going towards the right hand side, your model is usually like simpler model. Like it doesn't have like too many curves. There is the gradient is like better to find a global minima kind of thing. If you're looking for local minima, you'll just end up finding a global minima instead. So that's like lower complexity model. On the right hand side, we have lower complexity models. On the left hand side, we have higher complexity models. And that is the reason why we are also like looking for something in the middle with low error, obviously. It doesn't matter. You can definitely go down here a little bit if you want to simplify your model a little bit more to make it faster. But the thing is, you primarily want correct predictions. You don't want bad predictions. Variance is something which you can trade off with. Does it make sense to you?
Yes.
Okay, good.
एग्जैक्ट ट्रेड ऑफ का मतलब हमें उन दोनों के बीच बीच की चीज उठानी है. ट्रेड ऑफ का मतलब
Yeah,
ये
yeah,
हुआ.
yeah. Trade-off basically means either you choose this part or this part or somewhere in the middle, like कि यहाँ से थोड़ा सा ट्रेड यहाँ थोड़ा ले लेते यहाँ थोड़ा ले लेते kind of thing. So it's trade-off just means like it's a competition between both sides.
ठीक है.
You can choose one. So you can choose one point basically. You cannot choose
Cool.
both. Yeah. So this is the whole concept behind it. Like the bias and bias variance trade-off and no freelance theory, all same thing. There is no, I mean, this no freelance theory is primarily from algorithms, by the way, optimization of algorithms. But when it comes to machine learning, this is what it means here. So ये topic तो इतना ही सा था.
Ashutosh, so
Yeah,
if
yeah.
you want to explain like in one or two line for this uh, trade-off thing, so how will say?
Okay, so trade-off is, I mean, it's a balance between bias and variance, which helps us. Let me just write this because I'm going to give you guys these notes, right?
Mm-hmm.
So, trade-off is a balance between the following things, by the way, all of these things: bias or error and variance. This is the first thing. The other thing is complexity and simplicity. Simplicity of the model, है ना? So there is this, and speed as well. So fast and slow, fast and slow. So I mean, obviously these things come together in a package. So if complexity is high, then it is going to be slow. Simplicity is, if it's more simple, then it's going to be faster. So it comes in a package, but these are the things that you're balancing between. And of course, accuracy. I mean, that is what bias, variance, this is what like accuracy is like. Accuracy. This is what that is, right?
So in that graph, should we take that variance on x-axis? Like we have taken complexity, na?
Yeah, we've taken complexity on this axis, the complexity of the model.
So at a time, like we should draw the graph between bias, like bias and variance, and then complexity and simplicity, and fast and slow, like that.
No. This is going to be bias and complexity. This one is like error or bias versus complexity, and this one over here above, this one is more like variance and bias, and it is kind of more of like showing the result between the variance and bias kind of thing. Let me clean this up a little bit. I have created too many arrows. Okay, there we go. I'll just mark this. Okay, so this concept makes sense to you guys? Basically, you just want something in the middle, right? That's all you want to do.
Yes, sir.
Okay, good. Now we can actually move on to, so these are like literally three of these topics, this, and this. Let's move on to linear regression. Now, linear regression is like easy. If you're good with 2D geometry or 3D geometry, it's going to be very easy. And a little bit of statistics as well. So let's look into linear regression. Now I will quickly explain why of this. So what is it? Let's talk about that. It is an estimation of a function that represents all our data points. And that is what regression is. Like this is not linear regression, the definition of linear regression, but just regression. So that is a definition of regression. Now let's look at an example for this. A regression would be something like, say you have a few data points like this, over here, over here, over here, over here. So these are some data points, right? If you can find a function, Shilajit in my veins, playing Counter-Strike. Anyway, so yeah, if we can find a function, any function that represents all of these points like this, so you can have a function like this, that's like perfectly fine. And because of these curves, it's going to be like a higher order equation, like maybe like fourth power, fifth power, something like that, right? So this line, if it can represent these points, then that is the regression line of this. However, when it comes to linear regression, it's a little bit different. Linear regression requires that all the points are represented by one single linear line. So y is equals to mx plus c. That is what a single line, that is a line. That is why it is linear regression. Now, what does it do? Let's talk about why we do it. Let's talk about why linear regression. The reason for this is our data points. So our data points are discrete. Okay, do all of you understand what discrete and continuous is? Like, does anybody have any doubt in that? It's a very small concept. Okay, so I'm guessing nobody has any doubts. but it's a very small concept. So like if you have doubts, I can just explain it. So our data points are discrete, but our inputs that we want the prediction for, we want the prediction for may not exist in that data points, exist in those data points. So basically what we are trying to do, since because all of this, what we're trying to do is we are trying to find a continuous function. We are trying to create a continuous function, right? And let's look into a diagram and see what that does for us, right? So imagine there are like 1, 2, 3, and 4 data points, right? And I create a linear regression of this like this. That kind of makes sense, like they are like fairly equally apart from the line. So imagine this is our line, which is like y is equals to mx plus c. If our input was this point, right, then we already have this data point, and we can, by looking at this data point, we can tell, okay, the output would be this line right over here. So this is x-axis, this is y-axis. If it was this point, then we kind of know that, this point falls on over here. But what if we want to give this as an input, and this as an input have like this, has this point on the line? So with the help of this line specifically, we can, if it is a continuous line, we can definitely give an input from here, and we can get an output on the y-axis from here. Does it make sense to you guys now? Like, why do we do linear regression? We are trying to find a continuous function where we can give any input and we can like find any output, even though those points don't exist in our data point. So doubts on this? Okay, good. Riyansh has no doubt. Anybody else? Okay, good. So this is our primary goal for doing linear regression, right? Now, how do we do the linear regression? Let's talk about, we've talked about what it is, we've talked about why do we do it, and let's talk about how we do it now. So how do we do it? There are like points x and y. These are your features basically, right? This is going to be like, say, 1, 2, 3, 4, 2, 3, 4. I've just like made like random points, although these are like more of a line already. These are already a line, definitely. So how do we do this? First of all, we find mean of this. So we just want like mean. So basically, how do you write this? Like you write it as x bar, I think, and y bar, or something like that. So you find mean of 1, 2, 3, and 4. That is going to be 2.5, right? 2.5. And 2, 3, 4, and 5. What would that be? 14 by 4. That is going to be 3.5. Makes sense? These are the means. So far, so good, right? Good. Once you found the mean, you take the equation y is equals to mx plus c, and let's see, you can put, and you can pick any point. So you can pick like this point, you can pick this point, you can pick this point or this point, doesn't matter, whichever you want to pick up. So let's pick up like point 1 and 2. So that is like 1, 2. How do we find usually? Okay, so let's talk about in general, how do we find like m? In general, we find m by y2 minus y1 upon x2 minus x1. So any 2 points you can take, and then you can go ahead and do this to find the m. Like this is m is equals to this. But in linear regression, that is not what we do. What we actually do with linear regression is y2 minus y1 upon x2 minus x1 into, also multiplied by x2 minus x1 upon x2 minus x1, because this is basically nothing. We're just squaring this term at the bottom, and then we have a multiplication of these terms. So this term gets multiplied by this, above and below, and this just gives you the slope. The slope is given by, I think, beta 0. So that is what our slope is, beta 0, or which is also called the m, but beta 0 for regression. This is the formula for it. So let's take points. We do have multiple points, so we can take any point over here. But primarily what you want to do is you want to take these points over here. Okay, give me a second, by the way. I'm gonna get some water. I'm like, the throat is getting a little bit dry. 1 second. Okay, I'm back. So now, where were we? Okay, over here. So yeah, Mm, this formula, right? So let's look into this formula. So primarily, when you are given points, like usually when you're given points, you are going to just take 2 points and then you can find the slope of it. But when it comes to linear regression, you do it slightly differently. You're already multiplying x2 minus x1 and like x2 minus x1 like above and below over here in the basic formula of this thing. And the other thing that you need to do with this is also find, so this, let's talk about this right hand, I mean y1 and x1 part of this. So y1 and x1 and like x1 and x1, these terms are going to be your x bar and y bar, the means that we have found over here. So these are the mean, right? This is the mean and this is the mean. We are going to use these terms. So let's rewrite this formula as any y. So I'll just write it as yi minus y bar multiplied by xi minus x bar upon xi minus x bar, but this one is going to be whole square. Make sense so far? Now the thing is, we have the mean, so we have already calculated the means. Like this will go into this, and we already have this. So what are you going to put in yi and xi over here? We are going to take all of these, the one that are given, everything like all of these points, and we are just going to sum them together. So basically, you can put this over here, and that becomes your slope. And what you do is you basically just put mean and then subtract the mean from the point that you have. So if we take this example, so x is 1 2 3 and 4, y is 2 3 4 and 5, we will have something like x bar, this was 2.5, right, and this is 3.5. I'll just write it here. There we go. So this will become something like 1 minus 2.5, sorry, that is 1 minus 3 point, no, yi, right? So y is starting from 2, y is starting from 2, so we have to start from there. So 2 minus 3.5 multiplied by 1 minus 2.5, 1 minus 2.5, this plus 3 minus 3.5. So this is one term. This is basically this term, by the way. And then you continue to put on these terms. 3 minus 3.5 multiplied by 2 minus 2.5. And then plus, there was 2, so there's going to be 3 minus 3.5 multiplied by, no, that was 3 was already here, 4 minus, I'm like making a mistake here, because this is the y term, by the way, 4 minus 3.5 multiplied by 3 minus 2.5. Is this the highest? Let me check. Nah, 4 and 5 is there as well. So one more term plus 5 minus 3.5 multiplied by 4 minus 2.5. 4 minus 2.5. So that is the like numerator for us. This whole thing is the numerator, and then denominator is basically each one of these terms minus. So that is 1, 2, 3, and 4. So let's quickly write those. 1 minus 2.5 ka whole square plus 2 minus 3.5 ka whole square. Sorry, 2 minus 2.5, that's still x bar, plus 3 minus 2.5 ka whole square plus 4 minus 2.5 ka whole square. And this will give you one single term, that is the slope. So if we like kind of solve this, like how much would this be? I think it's going to be a little bit complex. Can somebody like do this on calculator? Anyone?
Can I take random value?
Just make it like x and y or something like that.
Yeah.
Okay. So imagine that comes out to be say x, and that comes out to be now. I mean, not x and y. Let's make it a and b. It will come out to be like say a and a upon b, right? And that becomes your slope. And that's the simple part, by the way. So that slope is in the that is y is equals to mx plus c. That part, that m part is the slope. Now we have to calculate the c part, which is the offset, or if you call it like intercept. So that one's kind of easy to find, to be honest. If you have found the slope, so you take the value of slope a by b, and then you have x and y over here and plus c. You take this whole term on this side, it becomes y minus a by b into x equals to c. And then all you have to do is you have to take one data point and put it here, and one data point and put it here. That's it. And the data point that you usually put in here is not going to be the whole, like one single row or something. That data point is going to be this mean and this mean. So what you do is y was 3.5, so 3.5 minus a upon b, and this x bar was 2.5. And that once you solve this whole thing, it will come out to be one single numerical value, and that becomes c. Right? So with this, you have m, you have c, and all you have to do is you have to write capital Y is equals to your slope. I think that is beta 1. So I'm just going to write it as beta 1, and mx. So this is m, so that is going to be capital X plus your c that you have just calculated, that is beta 0. That is the one, that is beta 0, I think. By the way, do confirm which one is beta 1 and which one is beta 0. I might be like confusing those two terms together. But in the end, you write this equation with the numerical values of beta 1 and beta 0, and you're done. That is a linear regression equation over here. Although this is single linear regression, by the way. Multiple linear regression isn't much harder. I'm not sure if we have it. But yeah, before we move on to multiple linear regressions, like if you guys have any doubts in this whole thing, by the way, so make sure you write down. I mean, I will obviously give you guys this whole thing, so you can remember this formula and kind of that implementation of that formula as well. So this formula is important for you guys to find slope. The other part is just simple, like you just do it in y is equals to mx plus c, and like you can find the offset of the equation. So no doubt, any doubts in this? Any doubts?
Yeah, Ashutosh.
Yeah, Mohit.
I think earlier you said that beta 0 is m. So if it is y is equals to mx plus c,
Hold on one second. Let me check. Linear regression equation. So where is a linear regression equation? Okay, there we go. There. So beta 0. So this one is with x. So beta 1 is the slope.
Okay, beta 1 is m.
Beta 1 is slope. So if I have made a mistake somewhere, this one is a slope, right? So yeah. This is a mistake. So yeah, there we go. That is beta 1. And have I written it anywhere else? I don't think so.
No, it was here only.
Okay. And this one at below, yeah, this one's fine as well. This one's beta 1 and this one's beta 0. That is
The
fine.
C will be beta 0, right? The
Yeah,
final
C is beta
value that
0.
you said, like
Kind
will
of
be single
think
value.
of it like, okay, here's the thing. There's an interesting part to this. If you have three components, three features, X, Y, and Z, what happens is you find a slope. That is, so for example, between X and Y, there will be a slope. So that one will go with X. So Y is equals to beta X plus, there is an offset C. I'll just write it as C. And then there will be a slope between X and Z. So X and Z, or Y and Z, sorry, Y and Z. So X and Y and Y and Z. So that one term will be just added over here as, I'll write it down over here, 1 second, plus. So this was C. And this other term will also be beta Z. That is what will happen. So what happens is we replace this C, just remember it like this. We replace this C with a beta, and this is an offset, right? So you start with 0, and you can like give this 1, and this you can give this 2, beta 1 and beta 2. So
Yeah.
what happens here is all the slopes are like numbered 1, 2, 3, and 4, and just the offset, because it doesn't have any other, this variable with it, just name it 0. No, like there is no logic behind it, but yeah, that is how you can remember it. So if there were like more features, so say A, B, and C were also features over here. So all that will be like is like plus beta 3 A plus beta 4 B, and so on and so forth. That is all there is to it. So let's quickly talk about multiple regressions here, and then we can like kind of end it for today. And I mean, the first unit will be over. So let's talk about multiple regression. So this whole process, by the way, this whole process that we have done between these two data points, right? What we will do is we'll create one more data point. So say uh, there is X, there is Y, and there is Z. There is 1, 2, 3, 4, 2, 3, 4, 5, 3, 4, 5, and 6. So these are the points, right? Like random example points. So you find X bar, you find Y bar, you find Z bar, and the moment you are done with that, all you have to do is you've done a process between X and Y, which was this whole process, finding slope between X and Y. You repeat the same process between X and Z. So as long as this is our input, you do X and Y, and then you do X and Z. Your input should be with all the features. So X, Y, X, Z. If Y was your input, then Y, X, and Y, Z should have been the thing. And if there was like one more feature, say A over here, you would have found A bar, and then you would have done X and A as well. But you wouldn't do Y and A and Z and A, right? Or you wouldn't do Y and Z together, because these are the things that these are the features, and this is the input. This is our main input. So that's why you do it with X. So the same process, which was, say, what was it? Say, let's do X and Z. So Zi minus Z bar multiplied by Xi minus X bar upon Xi minus X bar, and iska whole square. So this will be a slope between X and Z. This is the slope between X and Z. This formula will give you the slope between X and Z. So beta slope, that would be beta 2, or slope between X and Z. Make sense? Does it make sense to everybody? It's just you have to do the same thing between like more and more features. So this equation will come out to be, in the end, this equation will come out to be something like this. Y is equals to beta 1 X plus beta 2 Z plus beta 0. That's it. That will become the equation between three variables. This will be the equation. So basically you can keep on adding one more feature and one more feature, and you can do multiple, and this is called multiple regression. These lines, by the way, so if you were to write this in like a line equation, y is equals to mx plus nz plus c, this is what it is like basically. So as long as this exists in this equation, this cannot be plotted. or you have to remove either this or this to actually plot this line. Like it doesn't plot the line. If you go to Desmos calculator and try an equation out like this, it wouldn't plot it. Make sense? I mean, like, let's just do that, I guess. We can, nobody's stopping us from doing that. Desmos. Like I said, this calculator is like very much useful for us. So if you were to do y is equals to 2x plus 1, so that works. Plus if I were to do plus 3z, yeah. So it doesn't work, right? It doesn't plot. It says there is an error. If you add a slider to that, you can move that for z, but there is no x line. So this actually doesn't plot. How you have to plot it is going to be something more along the lines of y is equals to 2x plus 1 and y is equals to 3x plus 1. So that was 3z, right? 3z plus 1. So it doesn't matter as much, but 3z, and that is, those are the two lines that are plotted, and that is how you actually plot those lines together. Otherwise you can't do it. Like it's not possible to plot it in the same equation. It doesn't happen. Any doubt on that? Any doubt
So
on
that
that?
basically goes into
with-
3 dimensions, right? With 2x plus 3z.
Yeah, but you cannot plot it in like it wouldn't be like a regression in this one. You cannot
Okay.
regress it in just this. It's not like kind of not possible. So
Okay.
you have to like kind of lower the dimension and project it in like another line or something like that.
Right.
So that works, yeah. So yeah.
Where does is the error minimizations what they call the ordinary least squares? That is it somehow related to this, or it's a totally different method?
So you're talking about MSE, right? What is it called? You said least squared, right?
Yeah, least square minimization.
I'm pretty sure it's not about regression at least.
Okay.
But again, like I said, like I'm pretty sure. When I say I'm pretty sure, I mean like might not be, might be connected to it, might not be. So just in case, like when it comes to regression, I'm like kind of good at simple linear regression, multiple regression, and splines. But those are like pretty much it. Like I haven't done the optimization for this specifically to reduce the error. But yeah, in general, if you do multiple regressions, what you expect is like just this step in itself removes a lot of errors in general. Like it kind of brings it together to create a single line.
Okay.
Yeah. There is also one more way to kind of understand this by the way. Like that's like kind of like a mean of x, and so this is y bar and that is the x bar, say that is the mean of these two. So these two have like an intercept on both ends, right? Our linear regression line is probably going to like most likely going to be like in the middle and a perpendicular to this line, kind of like that.
Okay, that makes sense.
Yeah. The only thing is that offset is something that we have to calculate, that this line might go from here or this line might go from here, but that offset is calculated by giving the c, right? So how off it is from the center or from the origin, kind of thing.
Got it.
Yeah. So yeah, linear regression isn't hard at all. Like you just have to connect it to your 2D geometry knowledge, and then it is like perfectly like not a hard concept to do at all. So yeah, that's
That
yeah.
line, the line will be having multi-dimension and 3 dimension what you are having. So that will be in 3 dimension, right?
If you have multiple features, I say x, y, and z. Usually, when multiple regression, what you do is you do x and y first, and then you do x and z. So it's not in like higher dimension. But if you want to do higher dimension regression, in that case, you actually have to plot it, and there is a whole different process for 3D regression, or higher dimension regressions. That is like okay. So think of it like this, right? There is a vector, right? Say I'm gonna write a vector here. Say 1 and 2, right? This is a vector, right? What is the difference between this vector and say this matrix 1, 2, 2, 3? If I'll just put it like this: if this is like a vector which this is a combination of two vectors. If this was a combination of two vectors, then we cannot call this a matrix. We call it a tensor. But if it is not a combination of those, if like this vector is independent and this vector is independent, in that case it is the same matrix. But in that case you call it a matrix. You don't call it a tensor. So it's like, if you can add, it's the same thing as, are you going into higher dimension or not? Is your data, are you actually like interpreting it as X, Y, and X, Z, or are you interpreting it as X, Y, and Z? In that case, it becomes three-dimensional data. But otherwise, it is just like you're doing multiple regression on like pair of twos. In that case, it is like two-dimensional data. So it's kind of like that.
Because
Yeah.
why was I mentioning that? Because our intercepts value will gonna change in all three cases.
Yeah, definitely. And the intercepts values is going to be, this you will find it with, X bar, Y bar, and Z bar. You will be able to find it. It will remain the same between these two and between these two. All you want to find is beta 1 and beta 2. And beta 0 is like, once you calculate it, that works fine as is.
Okay.
Yeah. So, yeah. It is kind of like weird. Okay, I'm like we are beyond the class by the way now, so like don't need to record this. But think about it like this. Like I'll give you a question to think about. There is a line. What is the dimension of a line? It's a one-dimension thing, right? So it is a 1D thing. True. There are two things that you can do with this line when we are multiplying it with something. So you're multiplying it with say n. Say it was n was say 2, right? So you can multiply it by 2 by having this line going in this direction and then like another line going in the same direction. What it does is it doubles the length, right? Doubles the length. On the other hand, if you were to think of it as a scalar multiplied, this is just one quantity multiplied by another quantity, quantity 1, quantity 2, or you're just adding those two quantities. But if you were to just change your perspective a little bit from here and think of it as a vector, if you were to multiply a scalar into a scalar, say if you were multiplying it into 2 but in this direction, suddenly you have an extra dimension, right? There is a new dimension over here. Other than this, you also have now this dimension and you have an area. This is like what we are doing. Like sometimes you can multiply things. We can multiply x multiplied by y and both can be scalars and you can get a scalar out of it. Or you can multiply x and y. Both can be scalars and you can get a vector out of it. That is the thing between this as well. X, y, and z. This can be a vector in two dimension. I mean, this in itself, it's going to be the dimension is going to be three dimensions. So it's going to be like I cap, j cap, and k cap. But it will still be a vector. It won't become a matrix just by adding a new dimension to it. But if you multiply two vectors and then you kind of use them together to change something, in that case, it becomes a tensor, not even a matrix. Like it's even higher order. So you do know, like scalars goes into vectors, goes into matrices, into tensors, right? So how do we go from scalar to a vector, or how do we go from vector to a matrix? It doesn't always happen, but it can happen depending on your perspective and what you are trying to do. So as long as you treat this as two dimension, you can make pair of xy and pair of xz to do a regression. But if you want to do a 3D regression between these three, okay, here's the thing. There is one more very important thing, by the way. When you're doing regression, you're trying to find a relation between x and y. But if you're doing a 3D regression, then you're trying to find a relation between x where y and z are given. So y should be there and z should be there. On the other hand, just a regression is like, relation between these two. But this is a relation between a pair of these two and x. So as long as these are in pair, that is what 3D regression would be. And does that make sense? Like 2D regression and 3D regression? Riyansh?
Yes.
Okay. I mean, as long as it makes sense, like you have to kind of think of it like, going into higher and higher dimensions. And it's a choice that you have. Like you can go into higher dimension, it just means that these two will become like intertwined with each other, and दोनों के features हमको साथ में ही देखने हैं, that kind of thing.
क्योंकि ऐसा भी हो सकता है कि दो फीचर है, दोनों इंडिपेंडेंट है, बट नहीं फिर भी वो डेटा को क्लासिफाई कर रहे हैं, राइट? और
It is
एक हो गया दोनों का दोनों फीचर आपस में एक दूसरे ऊपर डिपेंडेंट है.
think of
Dependent
it
and independent features will decide the
think of
dimension.
it like a combination of events जिनके बिना हमें इसके और इसके बीच में वो नहीं मिल रहा है, कोई रिलेशन नहीं मिल रहा है. जब y z इकट्ठा ही होंगे, only then we find a relation between x and this z. So basically what we are doing is we are finding a relation between x and a set of features, or however many set you might put, but सबको साथ में होना जरूरी है उसमें. Only then you can find a relation, तभी ये होगा. But if we can find relation between single features, तो single features का ही करते हैं अपन, है ना?
कोई
Very
डिपेंडेंसी वाला कोई एग्जांपल देने जैसे सिंगल फीचर वाला तो अपन देख लेते हैं.
Okay, imagine this. Uh, let's try this, है ना? मतलब try करते हैं. I'm not sure example काम करेगा नहीं करेगा. But imagine if x, y and z are there. अगर x की there is certain value, तो we find कि y में there is no change. So change in x. Let's write it like this. Change in x does not translate to change in y. Sometimes क्या हो रहा है इसमें, जब x change हो रहा है, x is going up, तो sometimes y is going down. अगर x is going, sometimes क्या हो रहा है, x going up तो y भी ऊपर ही जा रहा है, तो y is also going down. Sorry, going up. So यहाँ पे दोनों एक ही डायरेक्शन में जा रहे हैं और यहाँ दोनों ऑपोजिट डायरेक्शन में जा रहे हैं. And there is no correlation that we can find between these two. But what if अगर ऐसा हो कि according to x की value and some formula, z gives you a value. So z gives you a value of z1, z2 and z3. If the value is z1, then there is no change in y. If there is the value of z2, then y goes down. And this z is dependent on x, right? We can see कि x is dependent on, like, z and x are codependent. But y and z are codependent, y and x are not codependent. Direct को हमें कोई dependency दिख नहीं रही है ना? So in that case, what you can do is you can do a 3D regression, and you will find this pattern. And that is what like deep learning does as well. Like it will find a pattern between x and z, and then pattern between z and y. But usually क्या होता है, हम regression में if we are taking x as a our primary feature, तो हम x के साथ ही y को बनाते हैं और x के साथ ही हम z को बनाते हैं, मतलब for our regression analysis, है ना? तो पेयर तो यही बनता है unless we are going into 3D और like deep learning वाला part, है ना? 3D में क्या होगा कि it will put all of these features on the same space, और उसी space में वो try करेगा कि relation कहाँ से जुड़ रहा है x, z और y का. So it will be like चलो x पे y मतलब x पे z dependent है और z पे y dependent है, then you can find it. तो इसमें 3D वाला काम आ जाता है regression. But that's like a मतलब primarily complex relations में ऐसा होगा. Like simple relations में नहीं होने वाला है ना? तो does it make a bit more sense, Riyansh?
Yes, sir.
Okay, good. चलो तो आज की क्लास इतनी ही करते हैं.
ये जो सिंपल लीनियर वन लाइंस हैं जो हम x और y और x और z में कर रहे हैं, तो ये क्या कर रहा है, ये सिर्फ एक लाइन बना दे रहा है x के रेस्पेक्ट में y x y प्लेन पे और एक x z प्लेन पे.
नहीं प्लेन सेम रहेगा. ये जो मल्टीपल रिग्रेशन कर रहे हैं ना, प्लेन सेम रहेगा. इट्स जस्ट दैट कि हम पहले एक्स वाई के बीच में ये वाला फॉर्मूला लगा रहे हैं, फिर एक्स जेड के बीच में ये वाला फॉर्मूला लगा रहे हैं, फिर एक्स ए के बीच में लगा लेंगे वही सेम फॉर्मूला. तो क्या होगा, हमें बीटा 1 बीटा 2 बीटा 3 बीटा 4 ऐसे मिलने लगेंगे हमें. तो वी आर कैलकुलेटिंग बीटा.
अल्टीमेटली अपने को जो बीटा 2 जो डिफरेंट बीटा 2 मिलेंगे, सो
बीटा 1 जो
बीटा
है
1 बीटा 1 बीटा 2 बीटा
हाँ.
x के लिए बीटा, y के लिए बीटा और x y x z और
एक्स वाई के बीच का स्लोप, एक्स वाई के बीच का स्लोप इज बीटा 1, एक्स जेड के बीच का स्लोप बीटा 2, एक्स ए के बीच का स्लोप बीटा 3.
and then all these slopes will be implemented on their planes of x y x z x z.
देखो मल्टीपल रिग्रेशन
समझ मतलब हम शायद सेम ही बात कर रहे हैं. मतलब रहना तो प्लेन ही है, पर लेकिन वो प्लेन में जब डेटा होगा तो x और y का, x और z का होगा, x और a का होगा.
हम यूजुअली जब इसको ना रिप्रेजेंट करते हैं लाइंस को, तो हम एक ही प्लेन में डाल देते हैं, एक्स वाई प्लेन में यूजुअली रिप्रेजेंटेशन में,
So
है ना.
how do we
बट
say
हाँ, देन
that?
अगेन इट इज जस्ट अ रिप्रेजेंटेशन. लाइक बात तो सही कह रहे हो, वो इट शुड कम इन इट्स ओन एक्सेस, लेकिन अपन यूजुअली रिप्रेजेंट करने में एक ही प्लेन में डाल देते हैं. प्राइमरीली रिप्रेजेंटेशन इज लाइक जस्ट अ प्रोजेक्शन, लाइक जो इट व्हिच मेक्स सेंस.
प्रोजेक्शन तो आएगा ही नहीं उसमें, जीरो ही आएगा एक्सेस.
लेकिन अपन बनाते जरूर है, पता है. दैट्स समथिंग दैट आई नो कि वो बनाते, वो लाइन अपन बना जरूर देते हैं एक्स वाई वाले में. खैर मतलब ये है कि दैट डिपेंड्स ऑन कि भाई टीचर बोलेगा कि ये सारी लाइनें दिखनी चाहिए, सारी रिग्रेशन लाइंस, तो फिर तो दिखानी पड़ेंगी. तो उस मामले में हो जाता है थोड़ा. बट अदरवाइज इट्स लाइक कि योर व्हाट यू आर सेइंग मेक्स सेंस कि हाँ, इसको अलग अलग डायमेंशन में करना चाहिए. हाँ, खैर एक बार somebody कंफर्म एक चीज कर देना थोड़ा सा, मल्टीपल रिग्रेशन अपन को है कि नहीं है.
सर ने
लेकिन
पढ़ाया
maybe
था.
सर ने
सर
पढ़ाया.
प्रोजेक्ट मतलब जब उसने टीए ने क्लास ली थी तो उसने एक सॉल्व कराया था डेटा सेट से लेके,
ओके ओके
जहाँ तक मुझे ध्यान आ रहा है.
ओके. तो मैं टीए की क्लास एक बार है ना, और एक बार रिकॉर्डिंग ही देख लूँ, ज्यादा सही है फिर
अरे
उसमें.
चल सर, रिकवर हो गया, कोई दिक्कत नहीं, आगे बढ़ते हैं.
नहीं नहीं,
मुझे
वो
लगता है कि इस पर
लॉजिस्टिक
कुछ
वाला
पूछा
है.
जाएगा.
इफ यू आर कंफर्म अबाउट कि वो लॉजिस्टिक वाला है, तो कल मैं लॉजिस्टिक भी करा दूंगा.
लॉजिस्टिक का क्लियर नहीं, आइडिया नहीं है सर. एमएलआर का तो समझ आ गया कि वो
हाँ.
उसने जस्ट डेटा सेट से करवाया था, फिर
हम्म,
स्काइट लर्न की लाइब्रेरी इंप्लीमेंट करके दिखा दी थी बस.
हाँ. अच्छा हाँ,
जैसे
मैंने टीए
रिकॉर्डिंग.
का वो नोटबुक देखा है. आई हैव सीन दैट नोटबुक जिसमें रिग्रेशन कराया है उसने. वो साइकिट लर्न वाला रिग्रेशन, तो इट इज इजी.
वो तो वही है जो आपने करवाया, साइकिट लर्न में वही यूज करता है जो आपने करवाया.
एक्चुअली मैं नहीं करता.
नहीं.
नहीं.
अच्छा.
इट इज लाइक थोड़ा सा वो है, क्या बोलते हैं, लाइक पीपल हैव दिस डाउट ओवर, मतलब कि कैसे एग्जैक्टली रिग्रेशन करता है. बट वो वाला जो रिग्रेशन है ना, जो साइकिट लर्न में, साइकिट लर्न, उसका एल्गोरिदम अगर चेक करोगे ना, तो यू विल फाइंड आउट कि ना वो, रादर देन फाइंडिंग द बेस्ट, देखो. हाँ अच्छा, ये भी ध्यान रखना एक चीज थोड़ा सा. ये वाला जो रिग्रेशन होता है ना, दिस मैथमेटिकल रिग्रेशन, दिस होल प्रोसेस जो है ना, दिस इज द बेस्ट फिट लाइन. इसको मैं लिख देता हूँ यहाँ पे, कहाँ लिख दूँ, रिग्रेशन के यहाँ पे लिख देता हूँ, है ना, बेस्ट फिट लाइन, बेस्ट फिट लाइन. ठीक है. जस्ट रिमेंबर दिस लाइन, बेस्ट फिट लाइन. व्हाई डू यू वांट टू रिमेंबर इट? बिकॉज अंडर फिटिंग एंड ओवर फिटिंग इज अ थिंग, है ना. तो अंडर फिटिंग वर्सेस ओवर फिटिंग, एंड वी आर टॉकिंग अबाउट समथिंग विच इज आफ्टर ओवर फिटिंग, विच इज बेस्ट फिट. ये वाला जो लीनियर रिग्रेशन अपन कर रहे हैं, मशीन लर्निंग में किसी काम का नहीं है. लाइक इट इज यूजलेस टू अस. मतलब इट इज नॉट यूजलेस, ऑब्वियसली अपन यूज करते हैं इसको, बट व्हाट वी वांट इज समवेयर विच इज लाइक काइंड ऑफ गुड फिट. व्हाट वी आर टॉकिंग अबाउट यहाँ पे इज 100% एक्यूरेसी, मतलब 100% फिट हो रहा है. अंडर फिटिंग जो होती, दैट इज अंडर 70% एक्यूरेसी, राइट, अंडर 70% accuracy. Overfitting is like over 90%. So if it is like over 90%, तो अपन उसको रिजेक्ट कर देते हैं. बिटवीन 70 एंड 90% हम अपने मॉडल को एक्सेप्ट करते हैं, नहीं तो हम करते नहीं है. तो बेस्ट फिट लाइन क्या होती है हमारी? बेस्ट फिट लाइन इज 100%. तो scikit learn what it does is it approximate down, ऐसे है ना, it will start creating a function धीरे धीरे करके, and it will approximate down कि exactly अच्छा यही वाली लाइन है, then finally, तो which is like good enough for our data. तो वो एकदम से है ना, ऐसे नहीं होता है कि साइकिट वाला जो एल्गोरिदम है डजंट फाइंड द बेस्ट फिट. इट फाइंड्स अ फंक्शन धीरे धीरे अप्रोक्सीमेट करके कि ये वाला फंक्शन जो है दैट वर्क्स फॉर अस, एंड दैट हैपेंस ओवर लाइक ट्रेनिंग, है ना. तो साइकिट वाला थोड़ा सा एल्गोरिदम अलग है. इट इज नॉट द सेम रिग्रेशन, बट काम यही करता है वो. इट इज डूइंग द सेम वर्क, बट वो यहाँ पे अंडर फिटिंग ओवर फिटिंग के बीच में काम कर रहा है ना. तो जस्ट रिमेंबर दैट. खैर, तो हाँ, दैट्स मोस्टली इट. ये फर्स्ट यूनिट जो है ना, दैट इज प्रिटी मच डन. इसमें एक टॉपिक आया है, जस्ट फॉरगॉट, अभी अभी थोड़ी देर पहले अपन चेक कर रहे थे. आई विल लुक इनटू दैट टॉपिक एंड आई विल कवर दैट. वो आगे भी काम का ही है. और कल आई एम थिंकिंग कि है ना, ये जो अपना PCA, LD, ICA, SFFS, ये वाले जो है ना, ये दीज आर ऑल न्यूमेरिकल्स. और ये लीनियर डिस्क्रिमिनेंट फंक्शन, डिसीजन, रैंडम डिसीजन ट्री, फॉरेस्ट, तो इट्स एन एल्गोरिदम प्रॉपर. अब अपन न्यूमेरिकल करेंगे कल से, है ना, बिकॉज वो अपन को असाइनमेंट भी जमा करना है, तो लेट्स फोकस ऑन दैट असाइनमेंट 3। ओके, चलो फिर कल मिलते हैं।
एक काम करते हैं, असाइनमेंट भी आ रहा है ना सबका,
हाँ
तो एक काम करते हैं, पहले वो कर लेते हैं, के मीन वाला कर लेते हैं, तो
ठीक है।
सबको
के
समझ
मीन
में आ जाएगा
क्लस्टर
सब।
कहाँ चला गया? के
गॉसियन,
मीन
ये है क्लस्टरिंग वाले में,
ये है, हाँ ये है।
के मीन क्लस्टरिंग, ये जीएमएम, गॉसियन मिक्सचर मॉडलिंग एंड ईएम एल्गोरिथम, ये तीनों
सो
को कंप्लीट कर
लेट्स,
लेते हैं कल।
हाँ तो पहले ये कर लेते हैं क्लस्टरिंग, एंड देन वी डू डिस्क्रिमिनेटिव मेथड्स, ये काम आएगा, है ना, एंड देन
या फिर
पैरामीटर।
कल क्लस्टरिंग पूरी खत्म कर देते हैं ना।
हाँ हाँ, क्लस्टरिंग
नहीं,
पहले पूरे इकट्ठे ही खत्म कर देंगे, क्योंकि वो अपन को है ना इसमें असाइनमेंट में।
कल खत्म हो
ये
गया
क्विज
तो
का
उसके
भी
बाद
है ना, इस बार के क्विज का यही है।
ओके,
इसने दी है क्या इसके लिए स्लाइड्स?
स्लाइड्स तो आई थिंक सारी हैं, बट वो वीडियोस अभी रिसेंट वाली नहीं डाली हमने।
नहीं, आई गेस इसने ना के मीन्स वाली ये दी नहीं है स्लाइड्स। लास्ट जो सर ने शेयर किया है वो आई गेस वो कर्नल वाला शेयर किया है,
हाँ
ये
वो
नहीं
तो
दिया है।
ठीक है, दैट इज नॉट एन इशू। बाकी अपन आई एम लाइक थिंकिंग ये लास्ट वाला जो पार्ट है ना, ये एएनएन वगैरह, दिस इज लाइक, क्योंकि अपन ने इतना प्रैक्टिस कर लिया है कि आई थिंक ये एक एक दो दो क्लास में सबको समझ में आ जाएगा जैसे समझाएंगे, तो ये वाला ना लास्ट के लिए छोड़ देते हैं अपन, डीएनएन सीएनएन ऑटो एनकोडर्स बैकप्रॉप एमएलपी,
हाँ,
ये सब।
ये तो लास्ट के दोनों चीजें अपना एक लेक्चर में हो जाएगा,
हाँ
फॉरवर्ड बैकवर्ड
और ये दो भी सर
रिवर्स।
ने कराए भी नहीं है, पता नहीं है वो कितना डीप में जाएंगे, है ना।
ये सर कराएंगे नहीं सर, बस सेल्फ के लिए रखेंगे, कहेंगे क्वेश्चन
हाँ,
करना है बस।
नहीं,
एक
सर ने ये एमएलपी करा दी है,
कुछ
परसेप्ट्रॉन्स वगैरह कराना चालू कर दिए थे।
नहीं अभी तो वो कर्नल मेथड्स पे ही है ना, वो जो
हाँ, कर्नल
कर्नल
पे तो
तो
है अभी।
शुरू भी नहीं किया है उन्होंने।
हाँ
हम्म।
चलो कोई बात नहीं, वो हो जाएगा, पता है, इट्स डोंट वरी अबाउट टू मच, अपन को तो अब मार्क्स से मतलब है अपने।
आरबीएफ नेट क्या है? आरबीएफ नेट में क्या होता है?
ये
आरबीएफ नेट,
आरबीएफ नेट, हाँ वही नेटवर्क का ही है, न्यूरल नेटवर्क्स का ही है।